Bill on a bridge.
The Brooklyn Bridge, pardon me, was the world's largest suspension bridge when it was finished in 1883. Bridges help us connect land to land. But what about connecting water with water? Whoa! Hey, I'm walking here!
A land bridge between North and South America.
Now, if I could just get to the other ocean here, it would save me months of travel around South America. That's what King Charles V of Spain thought in 1534. But the canal wasn't completed until 1914, after U.S. President Teddy Roosevelt sent thousands of workers to Panama to dig their way across.
Old film of a ship in the canal. Old world buildings and boats line a wide canal.
Canals are artificial waterways built to connect rivers, lakes, or oceans. Some canals carry water to irrigate crops, but the biggest canals carry ships filled with passengers and cargo. The earliest canals were links or extensions connecting natural rivers. One of the first was the Grand Canal of China, begun around 486 BC and finished more than 1,000 years later. It was an engineering marvel of its day. In the early 20th century, another great canal opened, also an engineering marvel. The Panama Canal cuts through 50 miles of dense tropical jungle and solid rock, creating a shortcut between the Atlantic and the Pacific that allows ships to go from sea to sea in just 10 hours. The canal provides ships with a much quicker and safer alternative to the perilous 7,872-mile-long passage around the tip of South America. Every year, thousands of ships are literally lifted across Panama's mountains by a remarkable series of water elevators and artificial channels. A ship entering the canal from the Atlantic Ocean navigates a locked facility of 3 chambers, or water elevators, that raise the ship 85 feet to the level of Gatun Lake. At the other end of the lake, more chambers lower the ship to sea level on the Pacific side. Lifting a massive ship with a mechanical elevator is an enormous challenge, but water does the job easily. The system works like this. The lock facility on the eastern side of the Panama Canal consists of 3 connected chambers. 6 locomotives guide the 65,000-ton ship into the lock chamber. Once inside, the gates close. In the control tower, operators turn valves releasing water from Gatun Lake into the chamber. Gravity pulls water from the lake and sends it into the chamber through holes in its floor and sides. The rising water lifts the ship to the level of the next chamber. The gates, each weighing hundreds of tons, open slowly and the locomotives pull the ship forward. The process is repeated until the ship rises 85 feet above the Atlantic Ocean. Then it's released into Gatun Lake. When the canal first opened in 1914, the size of the locks in Panama set the size limits for shipbuilders. New supercargo ships, however, are too long and too wide to fit through the canal's locks. If the canal is not expanded, it could gradually lose its importance in world trade. In October of 2006, Panamanians voted to expand and modernize the canal at a cost of more than $5 billion. The biggest engineering challenge to upgrading the canal will be building new locks, 3 times the size of the originals. 2 design teams will handle the project. An American team will engineer the canal's new locks on the Atlantic side, and a European team will design locks for the Pacific end. To build the locks in the soft, unstable rock of the canal's Atlantic end, the American team is considering technologies already used on the Monongahela River, one of the world's busiest waterways. Instead of building a massive dry construction site in the middle of the river, the builders of the Braddock Locks and Dam first built sections of the structure on land. Then, they floated them into the middle of the river where the pieces were assembled.
In animation, a component sinks underwater and fits in place.
A similar method might be used to build the Panama Canal's new Atlantic locks. The canal's new Pacific locks face a different problem: powerful ocean tides. Twice a day, the tides at the canal's western entrance rise and fall an average of 12 feet, putting enormous pressure on the gates of the locks at high tide. Gates for the new Pacific locks must be almost twice the size of the existing Pacific gates. The gates in the proposed design are already in use in a canal in Antwerp, Belgium.
A roadway tops the thick gate.
They roll into place across the lock chamber. But these would have to be much stronger to handle the high water pressure. Ships entering the Belgian lock are lashed to the lock wall to keep them stable. The water enters through a set of pipes that is simpler and more dependable than those currently used in the Panama Canal. Water is the engine that drives every lock system. But Panama's Gatun Lake does not hold enough water to lift megaships through a larger version of the type of locks used in Belgium. Fortunately, engineers can use a system of holding tanks that recycles water to operate the locks. When a ship on this canal in Germany needs to move from a lower elevation to a higher one, engineers release water from the top lock chamber. Instead of spilling out into the river, the water flows into a nearby holding tank where it's used again. If engineers build similar holding tanks for the Panama Canal's new locks, they might be able to lift and lower megaships with the same amount of water used in the current locks. Bigger locks and modern equipment will keep the Panama Canal working for many years. If the Panama Canal is fully expanded and upgraded, it will change the way many goods are shipped and the way many people travel, just as it did when it first opened.